Hi. In today's lesson, we're going to learn about the electron layers surrounding the nucleus of an atom. We've learned in class before that the nucleus contains all the protons and neutrons, and the electrons go in a cloud outside of the nucleus. And up until this point, I've told you that you can never exactly pinpoint where the electrons are located within the electron cloud. That's true. But what's also true is the electrons start filling in layers around the nucleus. I like to compare this to parking spaces around a store. If this is a store, you know the first spaces to get filled will be the ones right next to it. After those spaces are used up, you know that the spaces surrounding that will be the next one filled. And it's only at the very end, when nobody has a choice, that the electrons will go in the next layer outside of that. Also, just like a store, they can't all squeeze in, right? So this first layer only can hold 2 electrons, and then this layer can only hold another 8 for a total of 10. And then this one will be filled when it has 8 of its own for a total of 18. So when you have electrons around the nucleus, one of the questions will be asked is to figure out how many electrons go in each layer. And in particular, it'll ask about valence electrons, electrons on the outside. So let's take a look at a couple elements. Let's just start with magnesium. Now, if we look at our periodic table, we know that magnesium is element number 12. That tells you it has 12 electrons because all atoms start with the same number of protons and electrons. So, when we put in these 12 electrons, the first 2 we'll take in the first layer, and then we keep adding in the numbered order. So 8 or 7, 8, 9, 10. Now that second layer is filled. And then 11 and 12. So a magnesium atom is an atom that would start with 12 electrons. So you notice it completely fills the first layer, completely fills the second layer, and then starts filling the third layer. So that's where the term valence electrons comes in. It turns out what's really important is the number of electrons on the outermost layer that has them. So in this case, these 2 would be considered valence electrons because of the outermost electron layer that has electrons. All the ones in the layer below that do not count as valence electrons. Let's take a look at another element, fluorine. Now on our periodic table, we know fluorine is element number 9, so that means it will have 9 electrons. So, this is how the 9 electrons would fill in. You can see we'd have 2 in the first layer, completely filling it, and then we would fill our way up until we get to number 9. You notice that this second layer is not entirely complete yet. So, it's got 9 electrons total, but only these 7 on the outermost electron layer that has them would count as valence electrons. The other 2 do not. One last element to take a look at is lithium. Now, lithium is element number 3. So, you can see that we would have 3 electrons, 2 in the first layer and 1 in the second. That means that this 1 electron would be a valence electron because it's the only electron in the outermost layer that has them. Finally, last but not least, I want to take a look at hydrogen and helium. They're kind of unique. So, hydrogen is element 1. It has only 1 valence electron because, well, there's only 1 electron and it's in the outermost layer. Likewise with helium, helium has 2 electrons, and they're both valence electrons because they're both in the outermost layer that has them. Finally, the one last element I want to show you is argon. So argon is element number 18. So if we go ahead and do this, all right, we need to put on all 18 electrons. So here's 10, 11, 12, 13, 14, 15, 16, 17, 18. So here's how the electrons will look around an argon nucleus. And what you can see is that out of these 18 electrons, 8 of them are in the outermost electron layer. The other 10 do not count as valence electrons. Right? These ones are in the layers below the last one that is filled. So these are not valence electrons. Only these 8 on the outside are.